Okay, so today we're going to study differential equations and one method we can use to solve them. I want to just warn you that you should be careful where you practice solving differential equations. You might be mistaken for a terrorist. Right? This is like a real article, an Ivy League professor who was solving some differential equations on a flight, and somebody thought that that made him very suspicious. So don't let people see you doing it too much. Okay, so a differential equation is an equation involving derivatives of some unknown functions. So here are some examples of differential equations. They're just equations that have derivatives in them. dy dx equals negative x over 2, dy dx equals 0.02y minus 40,000 e to the 0.03x, dy dx equals negative y over 2. So it looks very similar to the first one, but this one has an x and this one has a y. And it can have second derivatives or higher order derivatives as well. So this is the second derivative of a function y minus 5 times the first derivative of a function y plus 6 times y has to equal 0. The solution to a differential equation is a function that makes the equation true. So let's look at part D, and we're just going to check. We're going to look at a couple of functions and say, are they solutions to the differential equation? So I didn't leave you any space to do this. This is like a last minute add-in. So we are going to look at y double prime. That's just a different notation for the d squared y over dx squared. Minus 5y prime plus 6y equals 0. And I want to check two different functions. My first one I'm going to check is y equals 5e to the 7t. I want to know, is this a solution to the differential equation? So just like when you first started solving equations for a number x, right? Once you have a candidate for the solution, you can plug it back in and see if it's true. So we have a candidate, yes? I just made it up. Yeah, so I just made up a candidate solution. We're going to check and see if it's actually a solution. So to check, I'm going to replace the y here. I'm going to replace this y with this formula. And then I'm also going to replace the y prime and the y double prime with their formulas, because I could figure them out from the given differential equation. Right? So y prime would be 35e to the 7t because of the chain rule. And then y double prime would be, I don't know, what's 7 times 35? Is that right? 245? Thanks. E to the 7t. Okay, so I'm going to plug these three things in and see, is this equation true? Does the left side equal the right side? So y double prime is 245 e to the 7t minus 5 times 35 e to the 7t. That's 5 times y prime plus 6 times y, 5e to the 7t. Does that equal 0? So 245 e to the 7t minus 5 times 35, 175, plus 30 e to the 7t. Does that equal 0? No. Okay, this is not a solution. Does not make the equation true if you plug it all in. All right, let's check another function, see if we can get a solution. Okay, this time I'm going to check y equals 4e to the 3t. So I'm going to plug in the y with, I'm going to replace the y here with the formula 4e to the 3t. I also want to replace the y prime and the y double prime. So y prime is 12e to the 3t and y double prime is 36e to the 3t. All right, so y double prime, 36e to the 3t minus 5 times y prime, which is 12e to the 3t, plus 6 times y, which is 4e to the 3t. I want to know, does that equal 0? Does the left side equal the right side? So this is 36 e to the 3t minus 60 e to the 3t plus 24 e to the 3t. Does that add to 0? Yes. 36 plus 24 is positive 60, and then you have a negative 60. So this is 0 e to the 3t. That does equal 0. So that means that that function y equals 4 to the 4e to the 3t is a solution. So solutions to differential equations are just functions that make the equation true. Okay, in general, finding solutions to differential equations is quite hard, right? So Avery asked me where I came up with that one that and I said I made it up. So the one that was true, I solved it. I came up with the solution by solving it. We're going to learn one technique today for solving a differential equation called separation of variables. If you can take a differential equation and get all the y's and the dy on one side, and all the x's and the dx on the other side, the differential equation is called separable, meaning you can separate the variables, x's and y's, onto different sides of the equation. For these equations, you can integrate each side of the equation separately once you separate. So we want to find the general solution to this differential equation, dy dx equals y squared plus xy squared. Okay, so I have dy dx equals, there's a y squared in both terms here, so I'm going to factor it out, and I'm left with 1 plus x. Now I want anything that has a y in it on the left, anything that has an x in it on the right. So I'm going to start by multiplying both sides by dx. We're going to treat this dy dx like it's a fraction. The dx's cancel, and you get dy equals y squared times 1 plus x dx. So all the x's are on the right. I've moved them all to the right-hand side. How do I get that y squared on the left? Divide by it, yeah. Divide by y squared, divide by y squared. So all the y's are gone from the right-hand side. And on the left, I'm going to write this just a little bit differently. 1 over y squared is the same thing as y to the negative 2. So I'm going to write this as y to the negative 2 dy equals 1 plus x dx. So the reason I wrote it like that is because the next step, once you have separated the x's and the y's, is to take an antiderivative of both sides. Take the integral of both sides. And having y to the negative 2 written like that, it makes it easy to use the power rule. Okay, so an antiderivative of y to the negative 2 is y to the negative 1 over negative 1. And there's a plus c, right? And then the antiderivative of 1 plus x is x plus x squared over 2 plus an arbitrary constant, some different c. We'll call this c1. This will be c2. Arbitrary constants. So remember, the solution to a differential equation is a function. Y equals some stuff. Right? So all I have to do now is solve for the y. I need to get this y by itself. So I'm going to subtract c1 from both sides, and I'm going to have negative y to the negative 1 equals x minus x squared over 2 plus some other arbitrary constant, c3, which is just c2 minus c1. But they're all arbitrary, so we can just give them new names. Multiply both sides by negative 1. Oh, that was a mistake. Thank you. Okay, so now I have y to the negative 1, which is the same thing as 1 over y, is equal to negative x minus x squared over 2. I could write minus c3, which is the opposite of some arbitrary constant, which is just a new arbitrary constant. So I'm just going to call it c4 plus c4. So I'm one step away here. If 1 over y is the right-hand side, how do I get y? Just flip it. Yeah, take the reciprocal. You could also think of it as you multiply both sides by y and then divide by what's currently on the right-hand side. So my final solution is going to be y equals 1 over negative x minus x squared over 2 plus c. Once I'm done, I'm just going to call my arbitrary constant c. Okay, so there is a constant in the solution. Maybe you called it C4, maybe you call it K, it doesn't matter what you call it. There's some arbitrary constant in there. That means that there is a whole family of solutions to this differential equation, one for each value of the constant. So there's infinitely many solutions here. We want to find the one particular solution that satisfies the initial value or the initial condition that y of 0 has to equal 1. So y of 0, that means plug a 0 in for all your x's. So you get 1 over negative 0 minus 0 squared over 2 plus c. That's supposed to equal 1. So 1 over c has to equal 1, which means c has to equal 1. Yes. The fraction? Nope. Nope, I had to take the reciprocal of the entire right-hand side. Yeah. Should be different than putting a plus c outside. So it's really, really tempting to circle this c equals 1, but that's not the answer. The answer is the function with that c plugged in. So the answer is y equals, the particular solution that they're asking for is 1 over negative x minus x squared over 2 plus 1. Okay, so we should note that separation of variables doesn't always work. If I wanted to solve dy dx equals x plus y, why is that? This is not separable, but the one we just did was separable. So let's just see what happens if we try to separate dy dx equals x plus y. Oops. Okay, so before we wanted all the x's on the right, we'll try to get the y's on the left. So I started by moving the dx over. So let's see, if I multiply both sides by dx, these cancel. dy equals x dx plus y dx, right? And then I want to move the y over. How do I get the y over to the y side? Okay, if I divide both sides by y, I'd have 1 over y dy equals x over y dx plus dx. Because I have to divide this y into both terms. I still have y's and x's on the right. Can I get the y out of there? Can't do it. Can't do it. I would have to multiply both sides by y, but then that's going to introduce a y into this term, right? So I can't get rid of it. This is not separable. I can't put all the x's on one side and the y's on the other. Okay, so in your pre-calculus class, you learned that a equals p e to the rt, was the appropriate formula to use for continuous growth, whether you're modeling a population of rabbits or money in a bank account. This example is going to prove that A equals PE to the RT formula works. So we're going to let Y of t be the size of a population at time t. It is common to model population growth by assuming that the population is growing at a rate proportional to its current size. So as the population gets bigger, the population growth rate gets faster, right? Because there's more interactions between the members of the population, so they reproduce faster. So we're going to suppose a continuous growth rate of 5%, and we're going to translate this proportional sentence into a differential equation. So the population is growing at a rate, population is growing, so its growth rate is proportional to its current size. So its growth rate is its derivative, right? The rate of change of a function is its derivative. So we're letting y be the size of the population, so its rate of growth is dy dt. And that is proportional to its current size. Do you guys remember what proportional means? It means a constant multiple of its current size, like k times y. K is some constant. In this case, the constant is 0.05 because it's growing at a rate of 5% of its current population. So its growth rate is 5% of its current population. Let's solve it. We can use separation of variables. So I want to move the y over to the left and the dt over to the right. So I'm going to have 1 over y dy. I'm just dividing both sides by y. And then I'm going to multiply both sides by dt. So I get 0.05 dt. Typically, it's easier if you have constants or coefficients to leave them on the t side. Okay, so I have separated the variables. I integrate both sides. What is the antiderivative of 1 over y dy? Natural log. This is ln of y plus c1. And the antiderivative of 0.05 is 0.05 t plus c2. Different arbitrary constant. Next goal is to solve for the y, get the y by itself. So I'm going to subtract my c1 and I get the ln of y is 0.05 t plus new arbitrary constant c3. How do you undo taking the ln of something? I want to get y by itself. Yeah, e, you don't raise it to the e to that. Yeah. So I'm going to do e to both sides. E, e. Raise e to each side of the equation. So e to the ln of y is y because x, e to the x and ln x are inverse functions. They undo each other. So I've got y equals e to the 0.05 t plus c3. It looks like I'm done, but I'm just going to do a little teeny algebra trick to make this look a little bit simpler. So this is a rule that you all know and use all the time. I'm going to use it in reverse of how we usually use it. When you multiply like bases, what do you usually do with the exponents? You add them. Yep. Here I have two exponents added. So I'm going to rewrite this as e to the 0.05 t times e to the c3. Right? Because now these are two like bases being multiplied. I would add the exponents. But e to an arbitrary constant is just a new arbitrary constant. So we're going to call this y equals c e to the 0.05 t. There's my general solution. And now I'm going to give you an initial condition, and we will use it to find C. So suppose the population size at time 0 is 100. So if I plug in a 0 for t, my population y is 100. So 100 equals c e to the 0.05 times 0, which means 100 equals c, because anything to the 0 is 1. So c is 100. So the formula, find a formula that models the population, is this formula, the general solution, but replace the c with a 100. Okay, so to reiterate, we already did some checking earlier in the lesson, but this is an awesome thing about differential equations. You can always check your answer by plugging back into the differential equation. So we want to check that our formula from part C, this one, satisfies the differential equation and the initial condition. So the differential equation was dy dt equals 0.05 y. And the initial condition was y of 0 equals 100. So the initial condition is easier to check. So let's see. Y of 0 is 100 times e to the 0.05 times 0. Does that equal 100? Yes. Check. All right, now I want to check the differential equation. I want to know, does dy dt, does the derivative of this function equal 0.05 times the function? So what is the derivative of this function? I'll just write it out. So it is 100 e to the 0.05t times 0.05 for the chain rule, right? Does that equal 0.05 times the original function y, 100 e to the 0.05 t? Yep, they are equal. So just a little bit of vocabulary and notation. A differential equation together with an initial condition is called an initial value problem. And I like acronyms, so instead of differential equation, I might sometimes write ODE, that stands for ordinary differential equation. And we might also abbreviate initial value problem as IVP. All right, that's it.